Hello, this is the first episode of what we will call writing system software, following DHH example that did very interesting work in the other part of the stack basically. This is about system software, so we will see lower level things, but the idea is exactly the same. That's to show in real source codes, not in small toy examples, how things work, why certain things were implemented in a given way. When software starts to become bigger, then the very clean approaches start to fail. You have to face compromises in order to make things work and use little memory and for the code to be fast enough and all this stuff. Today we will talk about the Redis append only file and how it is implemented. The append only file is basically it's a feature of Redis that allows to create a file that will log every write operation performed by clients, so that when the server will restart later, it will read back all these operations and basically rebuild again in memory the same data set that it had before being stopped. So let's start a Redis server with append only file enabled. In another terminal, we can check the content of the file itself as Redis populates it. Let's open yet another terminal and execute some operation. Okay, Redis CLI basically executed a command, and it's a client like any other client. So we can see that in the append only file we have actually the Redis protocol generated in order to execute this command again when the server will be restarted. We can see that actually we executed set foo bar, but there is also the select command, because basically I could change the currently selected database, so the select statement must be generated in order for the commands to target the database, and when the server is started, the currently selected database is set to unknown, so the first time the select statement will be created. And I can just type another command and see the corresponding protocol to be created. This is just Redis protocol. This means we have two arguments. The first is 4 bytes argument, the other is 9 bytes, and so forth. Now, if basically sorry, there is some debugging printfs because I was actually doing something about this code path. So let's compile again Redis for a second. Okay. So if I restart again the server, the information inside the append only file will be processed again, and I can see that my counter, we have back the values that we set in the previous session. Now, how all this is implemented? One interesting thing is that we don't actually have like the function calls in order to log inside the AOF inside every every Redis command implementation. For example, if I get the source code of the set command, that's what we used. As you can see here, we will process the arguments, and at some point we will perform the operation. Here it's implemented in terms of the set generic command because it has different entry points, like set nx, set expire, and so forth. There are different variants. So the set generic command implements the set operation with different operations and variants. And here is the actual command implementation. We set the key with the new value, and then we perform this operation of incrementing this server dirty. It means basically that this command performed some operation on the dataset. So this is our only interface in order to say to the Redis core that this command is a write command, so it should be logged in some way, should be propagated, and then we set the expire and whatever, and finally the command will send the reply to the client. As you can see, there is nothing like, I don't know, log in AOF set and the arguments. So how it's going to work internally? Well, it's very simple to check, because basically every command execution inside Redis is performed by a function inside server.c, and this is the call function. Call is the core of the Redis execution of a command. It has a bunch of flags because call is used in scripting or when you accumulate a transaction using multi and exec, and everything that will, at the end of the day, execute a command will use call as interface, so it must accommodate different needs, and so there are many flags. But the function itself, the prototype, is very simple. There is the client, and there are the flags. And what basically happens is, okay, let's use here as a whiteboard. I have my client, and then the protocol received by the client from the client is processed, so that I will have the client argument vector and the client number of arguments processed inside the client structure, that here in the call function it's called just C. So I have C argv and C argc. Argv will be like, I don't know, set foo var or something like that. Sorry, too many notifications. Let's quit Telegram as well. And argc will be 3 in this case. So call knows what to call, and it has a number of flags saying what it should do with this command exactly, what other things to do other than executing the command itself. For example, we can say that we want this command logged in the slow log, and we want to populate statistics. We want actually to write to the append only file, to replicate, and so forth. Normally we just use command call full, that means slow log, stat, and propagate. And let's say what actually call will do. So basically, okay, this is in order to send the command to clients having the monitor command enabled in order to check what the other clients are doing. Then we basically initialize a bunch of things, and this is the core of calling a command in Redis. What happens is that we basically set our dirty local variable to the current server dirty global variable, and this is the same dirty that is implemented in the command implementation itself. As you can see here, we have server dirty. So basically a global counter is the interface in order to see if the command produced or not a right operation in the dataset. Okay, so basically we check the start time and we finally call the function pointer that's associated with this command. C command is a function pointer that was resolved starting from the argv0 from the command. So set is inside an hash table of commands and it's resolved. And if we are here in the call function, it means that the command is already valid, it exists, the general form is valid, like the minimum and maximum number of arguments and stuff like that. Then we calculate the time that the command took in order to be executed, and at this point we can compute the difference in the dirty between the time before calling the function pointer implementing the command and the time after the command was called. So what's actually this server dirty thing? As we said, it must be incremented when the command performed any operation, but the amount we should increment it is proportional to the number of objects that the command affected. So, for example, if I don't know, if I increment a key in Redis, then dirty will be incremented by 1. But if I perform like a multi-set operation, then dirty will be incremented by the number of keys affected. So it should be like the measure of the number of changes that the dataset received. This is useful because the RDB persistence in Redis has a time and number of change trigger in order to understand if it's time to save a new snapshot. So it uses dirty. But from the point of view of the AOF semantics, the important thing is if dirty was incremented or not. And we can see that okay, we perform other things that are out of scope for our discussion here, but the interesting thing is here. At some point, this command must be propagated. It must be propagated in the AOF file if enabled, and it should also reach the slaves that are attached to our master. And what happens here is that basically, if dirty, the propagate flags are set so that the command will be propagated to the AOF and the replication sockets, the slave sockets. Now, I can have also flags that the commands can set in order to force the propagation of certain commands regardless of the fact that dirty was incremented or not. For instance, the publish command of pubsub, it wants to be propagated to slaves because the slaves can get subscribers to the same pubsub channels, but at the same time we don't want to increment dirty in that case, because we don't want publish to affect the RDB saving triggers. So for example, the publish command will set in the client flags client force replication. And basically the interesting thing from our point of view is here. If propagate flags is not equal to propagate known, then we actually want to propagate something, and we call finally the propagate function. That's the part that will really, the function that will really perform the propagation of this command. So let's find where this function is. Okay, propagate. It's like two statements function, feed append only file and replication feed slaves. So inside call we actually just have the logic in order to understand if we want to propagate this command to AOF or replication. But the actual work of propagating is just these two function calls, and we are interested in the first one, feed append only file, and what it gets is the command that's a structure that describes the command that we executed, the database ID that the client was operating and writing to, and the argument vector and the argument count. And those are exactly the old client argument vectors and client argument count of the client that executed the command. So we can check this function inside the file AOF. Okay, here it is, feed append only file. So what here is where basically this select command that we saw inside the AOF file was generated. If the current dictionary of the command executed is not equal to the latest selected database in the AOF, then we produce this protocol for selection of the database. Then there are special handling things about the expire command and set basically where there are relative times in commands. We want to translate those into absolute times, because if I set a key to have an expire of 1 hour and I stop the server and I then start the server again 30 minutes later, I want virtually the time continuing to pass. So basically I register absolute Unix times inside the AOF file. So here there is a translation layer, but basically at the end of the day what happens is cat append only generic command inside this buffer, and basically what this means just to translate the argument vector into the argument vector into the Redis protocol. We can check this as well. Cat append only generic command. But the interesting thing here is that our function, our feed append only file function, will just use a buffer. It's not writing to disk. It's writing nothing to disk. We have this buffer. At the end, we produced our protocol inside the buffer, and then what happens is basically that we concatenate this protocol that we produced inside a global buffer that's server.aof buffer. So basically in this function, we are just accumulating the protocol that we want to write to the disk inside a buffer. So you may ask why don't writing directly to our disk instead of having this buffer accumulating stuff. Well, the reason is very simple. So imagine Redis having 50 clients to serve at the same time. So basically things are like this. While true, because Redis uses an event loop. It's an event-driven program. So you can imagine it as an event loop where things are like read from file descriptors, wrote to file descriptors, and here commands are executed. So in the first two steps, actually those are not two separated steps. As I read from the file descriptors and I get protocols from the clients, I execute such commands. And later I will route this content to the file descriptor, so the replies that were generated by the commands will actually be received by the clients. So if in a given cycle of the event loop I'm reading protocols for 50 clients and I'm executing multiple commands for such clients, it will be really time consuming to call the write system call again and again and again and again every time I process some client command. So what I do instead is basically to accumulate all the replies, all the append only file protocol in a buffer while there are readable clients that I can process. And finally, when I performed a full cycle, a full iteration of the event loop, I can finally write the AOF buffer into the disk. Okay. In this way, basically, I'm optimizing things a lot, because write is a very slow system call. Moreover, when I need to also perform fsync, it's a much better reason in order to group together the clients and the write to the disk, as we will see later. But for now, let's see that normally fsync, for example, if it's configured to fsync every second, it's not part of this game, because basically there is a side thread performing this operation. But in general, otherwise, we really want to write a single time for multiple clients. So let's check the code about that. And this is the function that performs this work. Okay, flash append only file is the function that's responsible of getting this buffer and actually writing the buffer to the disk. However, it has an argument that's called force, because it's not always going to really do that work. It depends. Let's see why sometimes it may not actually flash the buffer to the disk. Well, to start, if the length of the accumulated buffer is 0, we return as soon as possible. There is no reason to continue to do anything. If AOF fsync is set, the policies, if the Redis fsync policy is set to be every second, what we do is basically is to check if sync is already in progress. Here we call a interface that implements some IO threading inside Redis, but this will return basically true or false, depending if there is a pending write. So if the policy is every second and we are not forced, we see if we check if there is already a sync in progress, because even if we called the thread in order to perform the background fsync some time ago, it's possible that this fsync is still in progress. For example, if the disk is busy, the fsync call can take very long time in order to run. So here basically see if still just 1 second passed or almost 2 seconds, because this difference must be less than 2. We don't write still to disk, because writing to the AOF file while there is an fsync in progress in the same file will basically block the write system call. We will not be helped by the kernel buffers, but we will actually block waiting for the kernel to fsync before it accepts more writes. At least in multiple versions of the Linux kernel, this is the behavior. So we say, okay, still we can manage to postpone this writing to disk, so we do that. However, if too much time passed, we cannot return, and we continue, and even at the cost of blocking is we are going to persist on disk. But in that case, we log this to the user. So we say, wait, your AOF fsync is not able to basically be accomplished one for each second. So we are here after 2 seconds, and we see that our previous second fsync call is still pending. So your disk is too slow, and we are going to get some latency problem here. And what happens, and this is basically the code path that's reached when we really finally can write to disk. At this point we perform the AOF write. It's just let's see, but it's just write iterated in case a short write is returned. Okay, so after the write is executed, we need to perform many checks. The first thing that we do is to call the latency hooks in Redis that will log latency events in different parts of the code, so that Redis is able to tell you via the latency using the latency doctor command what's going on with your server, why it's slow. And at this point basically we check for short writes, and in case we have some write error, we basically set an error condition so that the server will stop not accepting more write commands. However, if basically the fsync policy is set to always, this writing to disk and getting an error like disk is full or something like that is an error Redis cannot recover from, and at this point it exits. But instead, if it's a recoverable condition, because fsync is not set to always, we can just set this error flag and just throw errors to new writes till the situation is recovered again, like there is at this point, at a future point in time, space again, and we can continue. Okay, so basically that's, well, here there are many other things, like we have to track the current size of the AOF file, because we want to trigger a rewrite of basically its log convection when the file gets too big, because like there are operations like increment counter. So if people keep incrementing a counter, the AOF file gets bigger and bigger and bigger, but this could be rewritten as set counter. That's the same operation but compressed a lot of, in a single operation instead of multiple increments and so forth. So we need to trigger based on the space of the AOF. Okay. Last thing is group commits. So basically, when AOF is set to fsync always, we have to guarantee a given safety property. If client sends a write command like set foobar, it will receive the OK reply only after there was a successful fsync performed to disk. Data must be committed to disk before the client ever gets an OK reply, the green light. So it says basically, okay, you can stay safe, your data is persisted. However, to fsync for every client performing an operation will make Redis bound to the number of fsyncs that the disk can perform every second. That would be extremely slow. So returning to the example that we did before, if I have 10 clients and they are doing like set foo bar, client 1, client 2 is doing increment counter, client 3 is doing x add my stream foo bar temperature 19.5 degrees and so forth. What about waiting to send the replies to such clients, then perform the fsync, a single fsync for all the 10 clients, and at this point we can allow the replies that the commands generated to actually be sent to the socket. So Redis attempts to perform this. However, to make sure that this is guaranteed, it's a bit complex because there are multiple interactions between the event loop, the way the commands are dispatched, and so forth. That's the end of the first episode, and see you the next time with a new topic. Bye.